Two sessions today. This is session number 30, and in this session we are having eminent speaker today, Dr. Amrinder Singh. He is principal scientist in agri statistics at IARI New Delhi. So I think sir has joined, and we are tuning with him. So I request participants to kindly mute yourself, and one more request is that at the end of session they are requested to put their videos on so that it can be recorded and the same can be reported to IICT also.
Arvind sir, please confirm the A.K. Mishra ji sir is present.
Sir is present, but I think his mic is also on, but I think he is not.
Good morning, everyone. I'm present here.
Yeah,
Okay.
Good morning, sir. Good morning.
Good morning. Good morning, sir.
So, any PPT you want to share, sir?
Yeah, definitely. I have some PPT I have to share.
Okay, so we can just try it first so that we can smoothly run the session. So,
Okay.
if there is any PPT, you can just check it is sharing perfectly here.
I'm sharing.
Yes.
In between, can we introduce?
I'm just sharing. Just check
Yeah.
after sharing.
एक बार शेयर होने दीजिए ना, फिर कर लेते हैं। हाँ, और सर एक बार अगर वीडियो ऑन कर लेते हैं तो भी बेटर रहेगा, जस्ट फॉर फोटोग्राफ पर्पस।
My screen is visible to you?
Not yet, sir.
I'm just.
I request participants to put their videos on at the end of session. So,
What is the issue?
पार्टिसिपेंट से रिक्वेस्ट है वो अपना वीडियो है वो लास्ट में ऑन, अभी ऑन नहीं कर रहे हैं ना, अभी ऑन ना करके वो जब सेशन एंड होगा तब ऑन करेंगे। सो इट इज रिक्वेस्ट टू ऑल द पार्टिसिपेंट्स वो अपना वीडियो लास्ट में ऑन करें, अभी ऑन ना करें। सर इन केस देयर इज एनी प्रॉब्लम ना वी कैन शेयर इट फ्रॉम आवर साइड। आप उसको मेल कर सकते हैं, सर को भी मेल कर सकते हैं, या
ऑन किया है, स्क्रीन मेरी पीपीटी है यहाँ।
ये कुछ खोला है क्या?
यहाँ यहाँ होगी, इसकी डेस्कटॉप पे होगी ना। हाँ, इसको पीपीटी यहाँ से लेने होगी ना।
आ गया
ना, पीपीटी कहाँ है? पीपीटी लेना
नहीं,
होगा।
इसमें एंटायर होता है
हाँ?
एंटायर।
हाँ,
ये आप पीपीटी चलाएंगे ना तो पीपीटी है।
पीपीटी यहाँ है, ये देखिए। हाँ,
ये वाला
हाँ,
हो रहा है, शेयर हो रहा है।
एक बार पूछो उनसे।
सर आपका we can see the whole screen.
हाँ, screen is visible to you?
Yes, sir.
Yes,
It
sir.
is visible. Yes, sir. It is visible.
So should we start?
No.
Sir, just while we are starting, so I request Dr. Pankaj Kumar Tyagi sir to kindly formally introduce our guest speaker today to the audience. So over to Pankaj sir.
Thank you, Arvind sir. It is my great privilege to introduce Dr. Armendra Kumar Misra ji. Dr. A.K. Misra is presently working as a principal scientist in ICAR, Indian Agriculture Research Institute, Pusa, New Delhi. Dr. Misra received his PhD degree from JNU, New Delhi. He has more than 23-year experience as a scientist in research and training. He has successfully executed World Bank funded mega ICT projects, consortium of e-resources in agriculture as principal investigator and Rice Knowledge Management Portal as CCPI under National Agriculture Innovation Projects and presently associated with World Bank funded National Agriculture Higher Education Project as COPI. He has also worked as coordinator under BTISNet project funded by Department of Biotechnology, Government of India. As a postgraduate faculty, he is associated with teaching and guiding postgraduate and doctoral students. His book, Introduction of Bioinformatics, Basic Concepts and Application is very popular among the PG students as well as the doctoral students. He is a senior member of different professional societies like CSI, IACSIT, and ISAS, and presently Vice Chairman Computer Society of India, Delhi chapter. He has published over 50 research papers and articles in peer-reviewed national and international journals. His area of research and academic interest also included AI, machine learning, and big data analytics, as well as he is the full and vast knowledge of the related to computer also. So I welcome Dr. A.K. Misra sir kindly, uh, blessing your vast knowledge to participant. Over to Dr. Misra sir.
Thank you, Dr. Tyagi. Thank you again to your organization for inviting me for this faculty development program. So friends, today topic we are going to take a very hot area of research nowadays, that is big data analytics, and we will see how we can utilize that big data analytics in agricultural bioinformatics. So I think I'm audible to you and audible and visible to you.
Yes sir, you are audible.
Yeah,
Thank you.
you are audible sir.
So friends, just to start with what a big data is. So just to take the background, I'm just initiating the thing with per day, on daily basis, we are creating 2.5 billion, or we can say quintillion byte of data. Sometimes we are referring that as exabyte, that is EB. It is around 10 raised to the power 18 bytes of data. And 90% of the data in the world available today has been created in last 2 years only. Just imagine 2 years back, before this COVID pandemic, what the resource available today, what we are having today. 2 years back, it was only 10% at that. And imagine the future. After 2 years, what will happen? What the knowledge base we are having today is only 10%. After 2 years, it will increase by tenfold. Just imagine what will happen after 10 or 20 years. So I want to say that data is growing on daily basis. Is a with very rapid speed. So how to cope that data? Big data analytics can play a very important role, especially in agricultural and biological domain. So our today's lecture, we are focusing on big data and how to do the big data analytics in our agriculture research. So data comes on various forms, as you faculty, you people are knowing that data can come as a document. Sometimes we are sending data through mail, images are there, different graphs we are using, different videos. Video is definitely having very big size. Your personal information, data transaction on daily basis we are doing, and much more data is obtained from various new technologies are there. We'll discuss the new technologies in later slides. So how to define big data? Big data analytics is a modern techniques for what? Collecting, organizing, maintaining and analyzing our large data set. And why we are using this big data analytics? We have to focus to discover new patterns, and to uncover information which is hidden inside the data by using remote server, and definitely we are using this internet resources nowadays. So just to take the background, if processed data is information, processed information is knowledge, and nowadays we are living in knowledge era, and the processed knowledge becomes our wisdom. So this is the hierarchy from data to information, information to knowledge, and knowledge to wisdom. That is the flow. In real-time application of cloud computing, definitely we'll see a little bit of that. Now ranging from medical research to agriculture research, environmental services, maintenance and management of financial services, and many other fields. Any field you can imagine, there is application of big data analytics, and we are producing a lot of data. Nowadays, we are living in data explosion era. Okay. So here to define the big data analytics, I'm using this diagram, and 6 V's are very important. 6 V's of big data, that is very important to understand. So 3 parts are coming from your generic big data requirement, that are variety, volume, and velocity. And acquiring big data requirement is coming after entering the data into your system, and that are variability, veracity, and value. Here you can see in this slide, volume means what? Size of data. Like nowadays, gigabyte, terabytes of records are available. Archives we are using, tables, distributed files, means all the things coming under this volume part. Coming to variety, in agricultural and biological sciences, variety of data is available nowadays. That you can distinguish them as structured data, unstructured data, multi-factor data are there, probabilistic data, and linked and dynamic data is also there. So different variety of data we are using in our day-to-day teaching and research. Now coming to velocity. Velocity means a speed of the data. So data we can process in batch, real, or you can say near time. Different streams we are using, and transactions are there, different processes are there. So that comes under velocity. So 3 parts, this variety, volume, and velocity are generic big data requirements. And now coming to the acquired big data requirement, that is variability. Means data is changing on daily basis. Different models we are using, and models are changing. Such changing models are there. Linkages of data, integration of data, that comes under variability parts. Now coming to this veracity. Veracity means what? True worthiness. The data you are using, is it true? What is the authenticity of data? Origin of data, reputation of the data. What data we are getting nowadays? Is it original? It is reputed. Accountability. The data, who is accountable for that data? And what are the availability source? So these 5 things: true worthiness, authenticity, origin of data, reputation of data, accountability, and availability comes under veracity part. And now coming to the final 6th V, that is value. Value means value of data. What is value of your data? With the data, what we are going to do? For example, correlation. Sorry. Sorry, correlation of data. Simulation we are using. We are using the data for prediction, for different hypotheses, and for different events. So these 5 terms: correlation, simulation, prediction, hypothesis, and events comes under value part. So always, whenever you are discussing this big data analytics, always remember these 6 B's. Now coming to biological sciences, or you can say agricultural sciences, environmental sciences, any domain of biological sciences, biologists are joining the big data club. And with the event of high throughput genomics, we will discuss how through genomic data is generating. Life scientists are trying to grab with massive data sets, and we are encountering 3 type of major challenges in biological data analysis. That is what? Handling. How to handle the available data. Data is coming to you. How to handle that data? How to process the data? Because after processing of data, only we can generate information. So processing is very important, and sharing the information. The what data you are having, how to share that data with others. So these 3 things: handling, processing, and sharing information, is big challenge in biological data science nowadays. So how to handle? In handling the biological data, 5 very important factors are there. You know, I've already discussed in my previous slide, because in biological domain, data volume is very large. How to tackle with the large volume of data? Because nowadays, a small data set, definitely agree, on your desktop or laptop you can process, but suppose you are having gigabyte of data available in your lab, how to do the processing? So this is the challenge, that is large volume, how throughput data. Nowadays, especially in agriculture and medical domain, high throughput data is coming. So this is the challenge, how to tackle that data. Because our traditional database management system available today, today's world, are not capable to handle that high throughput data. That how to relate that data and link different data sets is also a big challenge. And complexity, because data is very complex, heterogeneous data is there. So large volume, high throughput, relating and linking of data, complexity and heterogeneity are 5 major challenges in biological science nowadays. So the previous slide, what I've shown, I've just, if you see here, this is in pictorial thing. I have to show these 5 things, how to the things are happening, like large volume data, high throughput data, heterogeneity of data, how to relate that data set, the complexity of data. In the slide, you can see these challenges and how to tackle that challenge. We'll see later. So friends, here mostly I think you people are coming from biological or biotech background. So here some figures I have just shown. What are the available data sets nowadays in public domain? So gene bank, I think everybody is familiar with what gene bank is. So see the entry in the gene bank, that is the number of entity in gene bank nowadays. And I'm again repeating that what data I'm showing here is definitely changing. Suppose I've compiled the data 10 days back, and after 10 days, you see definitely the thing is changing. So just don't rely this set. I just want to take example. Suppose you have 10-day back data. After 10, 20 days, today, suppose you are logging to the system and seeing this gene bank or DIP UCLA protein resources, the figure is changing because the data sets are generating on daily basis, and this is due to the exponential growth. This figure is changing on daily basis.
Solid-based pesticide fertilizer, chemicals,
Is everything okay?
Yes, sir. In between, some participants have unmuted itself, so I'm just finding him. Okay, sir.
Okay.
Now we are good to go.
So this is the gene bank. Hello.
Yes, sir. You're audible.
Okay. So this is number of interaction between protein in DIP UCLA. These are the gene bank bases. Just figures. Imagine the figure. That are billions of bases, millions of sequences in gene bank available. More than 1 lakh protein structure available in the protein database. If you see the pathway maps in CAG, around 500 pathways are available nowadays. Swissport, TREMBL protein resources. If you see, then million and billions of data bases are available nowadays. And all this Swissport and TREMBL collectively we can put in Unipro. So these are the different data banks I'm showing you. So this is very vast biological data we are available here, and that are scattered here and there like this. Now coming to very important part, the 4 layers. What are the layers? I have discussed with you the 6 V's. What 6 V's of big data are there? Now coming to the layers, 4 layer of big data is available nowadays. So data source layer. What are the source of data? If you see here in the diagram, data source layer is the lowest layer. This is the layer where the data arrives at your organization or your lab or your institution, and includes everything from your, for example, I'm taking the sale record, customer database. Suppose some commercial organization is using the different feedback, social media channels, different data sources as coming nowadays to you as data source. Then suppose you are having data, then how to store that data? So data storage layer, the second layer. This layer is where the big data is stored. Where to store that data? Sophisticated and but very accessible systems and tools have been developed for the data storage. For example, two example I'm giving to you, that is Apache Hadoop, that is distributed file system. Little bit on Hadoop we'll see later, and Google file system GFS for data storage. I think you people are using the Google Drive, similar to that is on cloud. Google Drive is there, and we are putting all that your data there. That is Google file system is one example of data storage layers. Coming to the third part, that is the very important part and focus of today's lecture, that is data processing and analysis layer. It is third and some most important layer. Here we have to find out something useful we need to process and to analyze. Data is there, what data to process, what information you want to take, and how to analyze that. So a common method in big data analytics nowadays, we are using MapReduce tool. So little bit on that tool, the MapReduce tool we'll discuss for this data processing and analysis layer. And the final and upper layer, that is the visible user interface, we can say that fourth layer is data output layer. This layer is how the insight generated through the analysis is passed on the people who can take action and benefit from them. Means this is the thing visible to you, the output that can the form of report, different charts, recommendations, figures, that comes under data output layer. So four layer, always remember: data source layer, the original source of data, how to store the data, for that data storage layer. Third and most important layer is data processing, how to do the analytics, that is processing and analysis layer. And fourth important layer, the visible to you, that is output data output layer. Here some exactly this slide I've taken from Current Opinion in Plant Biology. If you see here the number of bases, and this is the growth I have shown you for new genome updates, and techniques that ABL5, ABN50. This is graph, you can see the fluctuation, you can see. Actually, price base for DNA sequencing and synthesis is shown here. If you see this blue diagram, you can see the prices is coming drastically down. Nowadays, DNA sequencing has become cheaper. See the example starting in early 90s when the thing started, that data sequencing started. If you see 20 years back and see nowadays, up to 18 figure is here. If you see nowadays in 22, 21, 22, this thing is drastically coming down. Its price per data sequencing and synthesis is coming down. The short oligo sequencing price is also coming down, but not up to data speed and gene synthesis. Here, if in the yellow thing you can see, the prices are coming down. But DNA sequencing has become cheaper. The purpose of showing this slide is this is coming like that. This very important slide, actually the focus for whole big data analytics and that computational biology nowadays, the bioinformatics comes from this diagram, you can see. Again, I am taking this initiation from early 90. Early 90 we are taking because biotech come into a picture in our research and academia around 30 years back. And this is the historical trend we are showing you, the storage price versus this DNA sequencing cost. The next generation sequencing, you know that NGS, what we are telling today, it is a technology of mid 2000, 20 years back, the NGS thing has started, and this has changed the whole research scenario, especially in biotech domain, and now threaten the conventional genome ecoinformatics ecosystem. The whole genome informatics ecosystem has changed after this DNA sequencing techniques. So see here, earlier the pre-NGS era, you can see that is here the figure I'm taking, that is base pair per dollar, BP per dollar. That is pre-NGS. The data think was doubling time was 19 months. 19 months means around 1.5 year 1.5 year, the data, the pre-NGS data was doubling. And hard disk storage, that the thing to store that data, that is, that cost we can calculate in terms of MB per dollar, while doubling time was 14 months. So see here, the data was generating doubling in 19 months, and the storage thing and what the thing we are storing, what coming under 14 months. So what is not a problem, data was coming and the computational techniques are there to store that data. That computational world is growing in rapid speed. So that was not a problem. But here, see here, what happened 10 years back, around 2010, 9, 10, if you see the figure here, that thing has come. NGS data base pair was doubling, time was 5 months. Means every 5 months, the thing was doubling, especially that NGS data was doubling. And I just remember I have started my talk with that, data is doubling what time? In around 15 months. And here NGS data is doubling in 5 months. So just imagine, data is coming on rapid basis, but we are not having the mechanism to store, to process that data. So what is happening now? Huge resource of data is available in academia, in research lab, and we are not having the ecosystem to utilize that information and to process that, to discover, for knowledge discovery, and to generate biological wisdom. So the thing is happening like that. And this is how to tackle that challenge. For that, big data can play a very important role. Just coming forward. So in the previous slide, I have shown you the thing, what is happening in that NGS world, and what are the storage techniques available with us. So here, different challenges, what challenges we are having in after generation of that data, the data source we are having. That is, suppose a good amount of data you have generated in your lab. During your research, the field trial, you have generated a huge amount of data. And now your job to utilize computational biology, or you can say bioinformatics, to process that data. For that, the challenge, big data analysis, biological data analysis challenge, first challenge is multiple comparison issue, especially in biological domain, especially medical, environmental, and agricultural domain. High number of false positives are coming compared to true positive. I think this audience is knowing what false positive is, what true positive is, what precision, what recall. So I'm not going in detail of this thing, what false positive is, what true positive is. But just to for this lecture say, high number of false positive is available nowadays compared to true positive. So this issue is, we are saying, the multiple comparison issue. Second thing, high dimensional biological data. You know, biological data is high dimensional. From 1D to 4D, we are having 2D data, 3D data. If you go in protein, proteomics, all 3D data we are generating. So it's very difficult to discriminate between two classes of data. Suppose data classification on protein or DNA sequence you want to do, then it's really challenging to discriminate between two class of data. Or in simplest term, I can say, in biological data mining, classification become difficult due to high dimensionality of biological databases. Okay, a small and a large p problem. This is always a problem in research, because number of sample n is very small compared to number of parameter to predict, that is p. So n is small and P is large. So it's a small and large P problem we are saying, and this is true in case of any biological data we are using. Coming to computational limit means we are having your own computer, you are using your own server in your lab. Limitation of hardware, your RAM, number of processors is always a limitation. Every lab is suffering the problem of computation, that is limited hardware is available to you. On your server or your machine, RAM is limited. Number of processor, mostly on a single desktop or laptop, you're using a single process. processor. Suppose on server you are using 2 processor or 3 processor, but number of processor, if you increase the number of processor, cost will increase. So always a computational limitation is there to biologists during their data analysis. Now noisy high throughput data, just seeking during the lecture also some noise, some high is coming. This is true with noisy high throughput data. During data generation, noisy data, error, some data is always coming. So due to source of error, because the data, the real data source having some error, difficulty in controlling experimental parameters, because data you are generating subject to condition, your experimental parameter you are setting. So if you are, it is always difficult to control all the experimental parameters during the experiments, and it varies from lab to lab. In my lab, my experimental parameters are different. In your college, in your university, your experimental parameters are different. For then, for the same thing, our data may be varies. So this type of error is always coming. You are saying that is noisy high throughput data, and integration and multiple heterogeneous biological data. Integration is the issue, how to integrate multiple data sources, and you know the data is always heterogeneous, different type of data. So how to handle that multi heterogeneity of biological data and how to integrate them. The different forms of data are there, different pros and cons are there, redundancy of data is there. So this 6 thing always remember, and always mostly those who are involved in research, they are facing this issue, 6 issues: that multiple comparison issue, high dimensional biological data issue, a small and large problem, computational limitation, noisy high throughput data, and integration and heterogeneity of multiple biological data. So these 6 challenges is always there in any biological data analysis you are doing, either in agriculture, environmental science, in medical domain, pharma domain, we are facing. Now, friends, I have discussed about different different problems. What are the problems we are facing? What are the problems? We may say always only the problem thing you are discussing. This is the issue. This is the issue. This is the problem. This is the challenge. Then what is the solution? How to tackle that? For that, the cloud is one thing I'm going to discuss. Cloud meets the big data. Just think, the nowadays we are living in very chilly weather. Just imagine temperature is 45, 46 in Delhi or your nearby area. Then we are always facing monsoon will come, after rain the situation will normalize. So again here, after too much of problem, some solution is required. So here cloud come into picture, that cloud computing come into picture, and cloud meets the big data, and the scenario we're going to see the change. That means cloud meets the big data, and after that what will happen? So solution of big data analytics challenges is cloud computing. One solution is cloud computing. You can tackle all this type of biological problem during your data analysis. We can resolve using the cloud computing. And nowadays, always you people is very hot term. People are listening it. Go to cloud, private cloud, public cloud. This number of things we are discussing. How the cloud computing can work in our biological domain. Little bit, some slides we want to discuss on that. So, what is cloud computing? It is the method for storing and accessing data and programs over the internet instead of computer's hard drive. Means you are going to do internet based computing in place of your the data store on your computer's hard drive, because you know computer's hard drive have some limitation. Maximum what, 1 GB 2 GB data we can store in your system, but to tackle the huge amount of data you definitely require that internet based computing. So it's a type of computing that relies on sharing of computing resources rather than having local server or your personal device. Means here what we are doing, I'm not going to utilize my own system. Definitely I'm working on my system, but I'm going to share the computing resource through internet world. So we are, despite in place of using our local server or our personal devices, we are going to share the computing resource available in public domain, or you can say private domain. So the word cloud is used as a metaphor for the internet, and it is simplest term we can say big data. This cloud computing is nothing; it's internet-based computing. So net-based computing you are doing in cloud computing. Okay, different services are like available, such as different servers, storage, and application are delivered to the organization computer through the net. Okay, cloud computing is comparable to grid computing. We'll see what grid computing is. So cloud computing and is, you can say, is next big thing after the grid computing. Okay, so all computer in a network are harnessed to solve problem too intensive for any standalone machine. You know, suppose one big problem is there and we want to solve that problem. Then what will do? In our real life scenario, some complex research problem. So we are not going to solve it alone. In your group, in your faculty or in your team of scientists, everybody is taking some small part of the problem and resolving. Means we are sharing our knowledge to solve that problem. Same thing is true here in cloud computing. In place of single machine, you are going to utilize multiple machine to solve a single big problem. So see here, this is very important slide. If you see this diagram, this is client infrastructure at top and application, and the interface is internet. So your front end is client infrastructure. What infrastructure you are having in your lab, in your college, in your university, and through net different application we can manage. So management, security at backend. Backend application security management and application of services, different services you can utilize, cloud run types you can utilize, different storage, all the infra, all thing comes under this cloud computing architecture. So it provides a platform or service through internet, you can say. You need minimum hardware and software installed on your machine. Network may be LAN or WAN we can use, and infrastructure is deployed remotely and user can access to meet their need. As per your need, you can utilize that to resolve your problem and utilize that application. Now coming to see here, suppose you are having large data files here and cloud platform is here. In the cloud, definitely one firewall we are putting and your computers are here. Sorry. So through here cloud platform is there and you are putting your own computers and one firewall. Firewall is interface to, you can say, uh, prevent you through unauthorized access. Here, same thing, you are supposing this meeting, only the authorized user, we are giving user ID and password, and accordingly we are using this meeting. So similarly, this large data files through firewall are coming to your system, and cloud computing platform storage are managing all the things. Okay. Now coming to what type of clouds we are using. There are four major type of clouds. One is private cloud. Private cloud is what? It is used for a single organization and it can be internally or externally hosted. Suppose you are, just take example of my institute or your college or university. You are having your own network, and through that network every user of your organization is using all the resources, the hardware available to you, software, internet related things. So this thing is the private part, means single organization can use that, and you can host it internally in your institution, or you can externally host that thing to some other organization. Second thing, if you see public, that is provide for open use for the public by a particular organization who also hosts the service. Public you can use means, suppose anybody can use the resource of your organization, that is public. Just like public transport system, you can say anybody can go to metro, to buses, to utilize the services. So this is the public part. Private, you can say your own vehicle, your own car. It's only you, your organization, can use. And here public, we are giving access to others also. One mode is community mode. It is shared by several organizations, typically externally hosted at some third party, but may be internally hosted by one of the organization. Suppose number of small organizations are working in nearby. So what we can do? We can just share the resources. Some resource I am having, some resource we are having. So both can share. Some software I am having, some software you are having, and both can share. This is just like pooled car, we can say. If pooled car, Monday my car will go, Tuesday your car will go, and we both can use for our local transport. So this is the community type of cloud. And the fourth one is hybrid mode. Hybrid mode, mixing of private public, means you can say composition of two or more clouds, private community to public, public to community, you can mix, and you can jointly bond together, offering the benefit of multiple deployment models. And it is externally hosted as well as internally and externally, both way you can host the thing. So four type of cloud, always remember: private, public, hybrid and community. Okay. So friends, I've just discussed the grid computing part. So in grid computing, in early 90s, grid computing has come into the picture. In grid computing, what we are doing? Solving large problem with parallel computing. I think you people are familiar that what parallel computing is. Parallel computing, multiple processors are used in a single machine to perform different tasks. So grid computing was used to solve large problem with parallel computing. Second term comes is utility computing. Utility computing is what? You are offering computing resources as a metered service, just like Google, offering computing resources as a metered service. For example, we can take the electricity we are using at our home, the water we are using. What we are doing? We are paying utility bill for that, and on metered basis we are using that thing. What the meter reading will come, accordingly I will pay. So in utility computing, we are offering computing resource as a metered service. Whatever as per your use, you have to going to pay. As your use is less, then definitely you are going to pay less. Your use is high, you are going to pay high. So this is the metered service, and based on the excess of use, you can say. For example, that Microsoft Team, we can say, based on the license you are using now. Suppose you are taking a license, and according to the license, you people are paying. So as per your requirement, this is utility computing is there. Third thing is software as a service. So it is network-based subscription to different applications. Application, maybe net-based application, maybe some software, especially in biological softwares, you know, two type of softwares are there. The one is your available in public domain. Public domain, that are free resources. Open resource, we can say. Open sources are there. For that, you have to pay nothing, and everything is available to you. But suppose somebody is selling the software, biological software to you. Definitely we can. I think I'm audible.
Yes, sir, you are audible.
So software as a service means network-based subscription to application. Suppose for protein modeling, one example you can take. You want to do protein modeling, then what will do? Some softwares are available, like Modeler. Mostly people are using Modeler is freeware, so you can use that. Suppose some discovery, some one software is there, so that is paid based. So either you can pay that, or you can just subscribe. On my one computer or two computer to my organization, I need license for that, and accordingly as per license we are going to pay to them. So that is comes under software as a service. Software as a service, and accordingly for license you are paying. Then comes the fourth part, that is cloud computing. Means it is around 10 years back, 2008-9, the cloud computing has come in picture. Anytime, anywhere, access to IT resources, and it is delivered dynamically as a service. So in cloud computing, anytime you can use that, anywhere you can use that. I think those who are anybody from state agriculture universities in ICR domain are knowing. One Sera actually we have used. In Sera, what we have done, we have take subscription for all the journals, all the resources, e-resources available across globe, and we have taken that license for that. And based on that license, we have distributed it to all 47 state agriculture universities, the more than 100 ICR institutions, and everybody was using that. And we are paying at single place. So that is license-based thing. One example of cloud computing means purchasing at one place, your whole organization across country was using that. So your price will come less, and everybody, every scientist, every student can utilize that utility. So that has definitely enhanced our research productivity, because our student, our researcher, our faculty, our scientists have access to all the available resources at single place. That was not possible to purchase, because thousands of journal you cannot subscribe at in single institute because it's very costly. So in spite that, we have chosen that cloud model, and through cloud model we have purchased in one central place, and accordingly we have distributed based on the IP authentication to all the users. So this is one example of cloud computing. Now friends, coming to show you the what thing we are using in cloud, or you can say supercomputing facilities. Is anybody in your group is familiar with the supercomputing facility available with us at IRI? Anybody from agriculture, veterinary, fishery background? No one.
I can see, sir, no one is answering it.
Okay,
So
okay, okay. No.
probably, yeah, probably we don't have any
Definitely,
experience.
that is definitely better to me to share the thing. Ahsoka, actually we are saying that supercomputer is Ahsoka. That is Advanced Supercomputing Hub for Omics Knowledge in Agriculture. Full form of Ahsoka, Advanced Supercomputing Hub for Omics Knowledge in Agriculture. And this is India's first supercomputing facility for agriculture. And we are hosting at ICRI New Delhi. In our institute, we are hosting that. So just see the diagram. Here what we have done. Sitting at Delhi, it's one central place, all the super thing we are having, and with different nodes we have put. For example, NBPGR, I think you are familiar, that is National Bureau of Plant Genetic Resource, that is situated in Delhi. So that is dealing in plant genetic resource. For fishery genetic resource, we are having one institute in Lucknow, so NBFGR. Animal genetic resource, we are having institute in Hisar, so we are putting that. And National Bureau of here in Mau, and one center that is in Bangalore. So four institutions we have taken for fishery resource, plant genetic resource, animal resources, different microbes, and accordingly one center place we are putting the thing. Just see the how this model is working. So see the hardware configuration. So we are having 256 node Linux based cluster, and every cluster having 3072 cores. Mostly the servers you people are using in your organization having 16 core, 22 core of servers. And here you can see more than 3000 cores are there on each node, and having 256 nodes. And 16 nodes, that is GPU based Linux cluster. It having 192 CPU and around more than 8192 GPU cores with one master. And similarly, you know the master slab computing. Similarly, for backup part, one slab computing is also there. 16 node Windows based cluster with one master. 16 node Linux based cluster with one master, and each of the 5 domains of NABG, like in all the 4 institutions, we have put this one master. And one semantic multiprocessing SMP for high memory intensive job, and that is 64 core with 1.5 TB of memory for storage. If you see remember my different force layer, but data storage layer, we are using this SMP with 64 core with 1.5 TB of memory. So these are the hardware configuration. Coming to a storage, 250 TB of network attached NAS we are using. We are not using actually NAS we are using. And you for secondary SAS we are not using, we are using NAS here. 250 TB of parallel file system PFS, 200 TB to archival storage, means all the background storage we are using the archival storage here. 25 TB of NAS and 50 TB of PFS, and each of the 5 domain of NFVC we are using. For networking part, we have used 4 QDR based InfiniNet internet connectivity, and it is accessible on 10G, 100G, 1000G internet switches, and all the connectivity is through NKN connectivity. Those who are coming from academic different institutions, you people are also using this National Knowledge Network NKN connectivity. So all the things are attached with this National Knowledge Network connectivity. We can go up to 10G, 100G, 1000G Ethernet switches, different switches we are using. So this is the whole configuration of the supercomputing facility we are using for our big data analytics. Okay. Now coming to what the resources we are using here. So friends, for NGS, the number 2 is 2 number of software for next generation sequencing are using. Similarly, for phylogenetic analysis 3, sequence analysis. For sequence analysis, we are using 15 softwares. For motif identification, having 1. Snap analysis, 2 software. For RNA analysis, the number showing the number of software or number of tools available on our facility. Protein expression analysis 5. Genome analysis 13. For gene analysis 2. Okay. So if you see here the number, these are the software available to, and all the software are open source software and tool are configured on the HPC environment to carry out various biological data analysis. And all these 52 tools are public domain tools. We have just collected one place, and it is accessible to our users. That is totally free. So here the cloud computing past, present, and future. I'm just skipping this slide. So 4 models are there in cloud. That is very important. 4 models. Service model define the type of services. So if you see here in bioinformatics cloud, 4 models are there. We are saying YAS, PAS, SAS, and DAS. What they are? DAS means public databases. All the public data sets, biological databases comes under DAS. Means data as a service. DAS means the data as a means as a service. Here you can see software as a service. The software means what? Different pipeline, different tools. So software as a service. PaaS means platform as a service. Here we are using analysis platform and different programming environment we are putting in PaaS. And the final one is YAS means infrastructure as a service. In infrastructure as a service, we are putting different virtual machines and virtualized resources. So always remember these 4 clouds part: DAS, SAS, PaaS, and AS. See here, this is service provider. Service provider are there. The cloud thing is coming with it is service provider. And through the service provider, software as a service, platform as a service, infrastructure as a service. If you see here, consume, software as a service means consumer level we are using this. Build on IT. Build on IT means all the IT infrastructure what you are putting in your organization, we can take as a cloud. Means we are saying that platform, all the platform we are using as a service. And here migrate all the things to it. Means infrastructure, all the infra you can put on cloud. So this type of thing means any infrastructure is not required or end. Just utilize that cloud infra and you can do everything. So coming to different characteristic of a cloud environment, what a cloud environment should have, it should be dynamic. One of the key to cloud computing is on-demand provision. What is your demand? Accordingly, provision is there to serve you. It is massively scalable. Means what? The service must react immediately to your need. Suppose your requirement is less today, you can use the small part. Suppose tomorrow you have to do big data analytics, number of data analysis you have to do, then definitely the thing will scalable and we will take the much resources for that. Multi-tenant cloud computing, beauty of cloud computing is that by its nature it delivers shared service. Means multi-tenant, number of people can use. I can use at my place, you can use at your place, and with the same software you all can work. It is rapid elasticity. You can go from 5 server to 50 or from 50 to 5. Suppose your requirement is high, you are going to handle some students' work, or you can say number of research projects you are handling, so you require much server. So you can increase the server. Suppose requirement is less in your during semester break or sometime your requirement is less, so you can come to less servers, less services. So it is elasticity, rapid elasticity is there. Self-service, as a user, you can use the service as you require. What is your requirement? Number of things are there, but everything is not useful for you. So you can choose what is required for your teaching, for your research, and accordingly you can take the self-service. Per user based pricing model. Pricing model of cloud computing is that as per your requirement. Suppose you don't require proteomics part, only genomics you are working, so only choose the genomic part and you are going to pay according to that. So you don't require to purchase the whole bundle. In place of that, you can just select your tools. This tool is required to me, that tool is required to me, and accordingly the price model is decided. And it is IP based architecture, means the thing will come to licenses come to your machine based on your IP, because you know every machine having their own IP. So through that IP authentication, you can use that. So these 10 features I'm again summarizing in this slide. This is resource pooling, one demand self-service, easy maintenance, large network access, availability of resources. This system is autonomic system, very economical, secure, pay as you go, because it is based on your payment model, and measured services. So these 10 features are there in cloud computing. See here, just to what we have discussed in big data sources, data analytics, and cloud computing. Here in the single slide, if you see, because everybody know input after processing become output. I think everybody from school days we are learning any input after processing become output. So here the inputting part, the big data source from where I started my lecture, that are what? Different variety, velocity, volume, variability. Any we can imagine veracity, visualization, value, virtuality, means for what? Structured data, unstructured data, semi-structured data, means, and coming through client web browser, mobile devices, we can use it. And data analytics, what we are going to do? Different tools are there, analytics tools are there, Hadoop is there, MapReduce is there, RDBMS, the traditional data management systems we are using, that is RDMS mostly, Oracle we are using. NoSQL is widely used in big data analytics, because RDBMS, that relational database models, are suitable for a small data set. Definitely we are using that, but for big data sets, that structure and tabular set will not work, because you know heterogeneity of data, integration of data are issues. So we are using NoSQL part. So sometimes here RDBMS SQL is working, but here for big data NoSQL. Here cloud computing and different service providers like private, public, hybrid. Again, the thing I've discussed in background, that infrastructure as a service, software as a service, platform as a service. So just what I've discussed here, I've just summarized these are the sources, these are the analytical tool, and these are the different platforms. Okay, from front end to back end. Now, friends, those who have working in sequencing lab, and what is the scenario, just in this slide you can see different sequencing labs are generating sequencing data. Those, because at our institute, our biotech department, we are also working on different sequencing projects like rice sequencing, tomato sequencing, which number of sequencing work are going on in our labs, and different scientific groups are working on that. What we are doing after sequencing? Anybody? After sequencing, what you people are doing? Definitely we are putting the thing to NCBI for storage. Your data will go to NCBI. Hello?
Sir, you
Yes, sir.
audible?
Yes, sir.
Definitely your data is going to NCBI, and after the NCBI, sequencing archive number of value added integrators are there, like ensemble is there, UCS is there, and they are integrating, and accordingly as a user sitting here as a researcher, you are visualizing the thing. Suppose you are a smart user, you are a good user, then what you are doing? You are not coming to this value added integrators like ensemble and UCBS. Directly we can access the thing through sequencing lab. Thing has come to NCBI, and directly as a power user you are using that. And simple user, what they are dependent on this value added integrator like UCSC, ensemble. So this part we can escape as a smart user, and you can directly take the resources from NCBI also. What are the new genomic informatic ecosystem based on cloud computing model? See here in this slide. What are the difference? Actually, two type of users are there. Those who are using the bioinformatics part, one casual user and power user. See the thing, because everybody is using the sequencing lab data, because that is the only data source. So you have two options: continue downloading data to local cluster, as earlier we are doing. What we are doing from NCBI, we are just downloading the data to our cluster, to our machines, and accordingly we are using that. Or you can use cloud computing, move the cluster to the data. Cloud computing, what cloud computing will do? Move the cluster to the data. The cluster, that is virtual cluster, if you see here, this is the sequence archive. So virtual cluster we are putting to the data. Suppose you have created a cluster through cloud, and the cluster will go to the data. This is the power utilization. And earlier days, what we are doing? Continue to work with the data via web pages in their custom way that traditionally we are using. Go to NCBI, take the data, put on your local cluster and use that. So see the change. What after cloud computing situation thing will change, because virtual cluster will go to that data. See here in virtual cluster. Friends, here I've compiled all the cloud resources available in bioinformatics domain, and we have categorized that in 4 parts: data as a service, software as a service, platform as a service, infrastructure as a service. And all the resources I've given some link also. Suppose some published and published data, all the resources I have compiled in one single slide for your access and use. Anybody who is interested to work on Hadoop or RNA sequencing or anything, you can take the link and you can do the practice, and you can say the beauty. And that is free. Mostly the resources you have given is free. Just through your web browser, you can go there and you can use that. So this is very important resource available to you to initiate with big data analytics for your research work and use some cloud flavor in your work. Coming to issues in bioinformatics, big data, some issues are there. What are the issues? Big data generation, and it gives birth to profound challenge for storage, transfer, security of the information. So just to share that big data storage space will be needed by companies. So storage is a challenge. It's a big issue, because how data storage space is a challenge. Another challenge is to transfer the data from one location to another. How to transfer the data, because internet speed is the issue. Due to internet speed, your transferring of data and other thing will be facing problem. Security and the privacy of data. Mostly people are saying is my lab data, how I can going to use that on that some cloud, because people will access my data, it's my research work, it's my very confidential data, personal data. And so this type of things are there in security and the privacy of data. And the situation has changed nowadays, because in cloud also your security purpose and your privacy of data is taken care of. because in our government setup, government funded, public funded research organizations, universities, we are having this thing, no, I'm not going to host the thing on cloud because it's my personal organizational data we will put on our servers only. But now the thing has changed, and trying to discuss here. Nowadays, government cloud has also come. Government organization, research organizations are putting their own cloud that NIC is also hosting. National Information Center, NIC is also hosting all the things in their data center, and that is very safe and secure because data is stored here in country only, and it is not going to US or UK for storage. And for our agriculture setup, we can say in our agriculture universities, our ICR institutional data, we are planning for Krishi Meg. Krishi means agriculture, Meg means cloud. Krishi Meg we are trying to put on Krishi Meg all the resources available in agricultural domain, especially in plant science, veterinary science, animal science, dairy, fishery, all the thing we can want to put at one place in a centralized cloud, and accordingly all the resources can be shared and integrated. So this thing on this thing also we are working. If you permit, then a little bit on some software also I can discuss.
Yeah, please, sir.
So coming to software as a service. So bioinformatics requires a large variety of software tool for different type of data analysis. So software as a service, cloud delivers software services online and remote access facilities. So as a concept, eliminate the need of local installation and ease, because problem what biologic we as a biologist we are facing, how to install the thing, because we are not IT savvy. So we are facing who will do the installation, the path setting, this, that. This in place of that, if thing will be ready-made, that is very become very easier. Suppose some ready-made thing will be there that is very accessible, like the Google link, Zoom link, and this Team link is very easy. Suppose you are giving, and accordingly we are sharing. So this type of thing now people wants. Thing is accessible to your desktop. So this SaaS model provides you being very accessible. Just install the thing and start your working. So effort has been made to develop cloud scale tools, including for sequence analysis, because the biggest job what we are doing in bioinformatics, biological bioinformatics, sequence analysis is mapping, assembling, alignments we are doing. For genome expression analysis, homology detection, peak colors of chip sequence data, genome annotation, identification, snap for NGS. This is the measure you can just categorize the thing why you require these services. Only for this type sequence analysis, gene expression, homology, annotation, identification, NGS. Purpose of bioinformatics, or you can say computational biology, is only to do this 4-5 things mostly we are using. So who are the cloud computing service provider? So cloud computing platform have been emerged in the commercial sector, like Amazon Elastic Compute Cloud EC2 is a platform
Sir,
that, yes,
sir, may I interrupt in between? Actually, we are getting two voices simultaneously.
from my
Okay.
side.
Yeah, sir, it seems like it is coming from your side because it is not from any other participant side. Maybe from
Because I'm
system.
sitting alone in my room and nothing is disturbing. I'm
Oh,
just
that
closing my door also. Let us see 1 minute.
actually, actually on system, if another window is open, please check. There's some.
Now it's okay. I've closed my
Like
door.
I can listen to another voice also.
From here, my side.
No, sir, it is coming continuously from other side. I don't understand from where it is coming.
Maybe. Now is
Oh,
it
okay,
okay?
sir. Okay, sir. It's okay. It's okay. It's okay,
Okay.
sir.
So some cloud sources I was discussing, Amazon Electric Compute Cloud, that Megaland, Diag. These are some example of cloud service provider. Increasing valuable tool for processing large data set, and already used in US, mostly that Amazon, DAG, Magellan. So Amazon Cloud Service, if you go, especially in for biotech, so we are using image processed by Galaxy. Galaxy is a very important service. Bioconductor. Bioconductor is giving you programming environment with R package. R mostly we are using for our analysis, that is statistical package. So this is providing programming environment that is bioconductor. G browser, this is genome browser. So we can create through that cloud browser. BioPerl is one programming environment, mostly Perl we are using. So BioPerl is just a pack for biologists to make their programming easy. And NCBI cloud is also giving us BioLinux. You know the Linux operating system widely used in open domain environment. So for biologists, BioLinux is also there. So complete copy of gene bank, all the genome projects, all are available on the cloud services. And now coming to pros and cons of cloud computing. What is the, because every good thing having is also involved with some bad things. So in what are pros and cons of cloud computing? As it, what is beauty of that? As it requires large data transfer over precious low bandwidth. Suppose you want to transfer very huge data, but your low bandwidth is there, noise is there, errors are there, then it creates problem. Raise new privacy and security issue. I'm not going to discuss that all the privacy and security issues, but that is always a concern nowadays in cloud world. What are my privacy? What are the security? And it's inefficient solution for some type of bad problem. I cannot say, you cannot say fully every bioinformatics problem we can solve with cloud computing. Definitely some part we can say, but no one can say 100% go on cloud computing and everything will be resolved. Nothing like that. But definitely it is a helpful thing to do. You can say 70%, 80% work, but not 100%. I cannot say through cloud computing everything is you can do, but definitely your basic thing, what you are doing, your analysis, homology, modeling, annotation, definitely we can use that. It is an incredibly valuable tool for processing large data set. Already US mostly research labs are on cloud mode. Pharma industry, internet company, scientific lab, bioinformatics services, that is some domain where cloud computing can play very good role in big data analytics. Some progresses in cloud computing for bioinformatics is HTTP based web service technologies. In some examples are simple object access protocol, that is SOAP we are saying, representative state transfer, that is REST services, BioMobi, and this is important due to the open extension, that is extensible messaging and present protocol. Now we are using that HTTPS protocol for our services, HTTP, or for security HTTPS protocol. But here the protocol we are using in cloud mode, that is XMPP, extensible messaging and presence protocol. SOAP that HTTP and XML provide a solution. So SOAP is simple object access protocol. So I'm just escaping this little bit, some flavor I'm giving, because focus is just to introduce the basic thing, combining everything. This for data analysis, some tools, just terminology wise, I'm just focusing you. SOAP, REST, I've already REST, representative state transfer. BioMobi, I've already discussed, an open source biological web service proposal. And in place of relational database management system, NoSQL is widely used in this big data analytics. Hadoop is a tool nowadays. The number of organizations are doing some training program of Hadoop. So Hadoop is a very, very good tool, and I think in the type of NoSQL distributed database HBase we are using here, and this is very good tool. When I'm always suggesting the young people, young faculty in our biotech domain to learn little bit of Hadoop, that will definitely enhance your productivity, research productivity. a Hadoop ecosystem comes in terms of MapReduce. In Hadoop, try to learn MapReduce, a computer model tech intensive data processing and spread the computation across the potential endless number of servers, as a, you can say, Hadoop cluster, and it has been a game changer in supporting the processing need of big data. A large data procedure might take 20 hours of processing time, or a traditional centralized relational database system may take only 3 minutes. So say that the speed, the for processing, if you require 20 hours, through Hadoop MapReduce, only 3-4 minutes we can do that through that Hadoop cluster. So MapReduce in Hadoop is a very important tool to learn. MapReduce is a software framework, and it is introduced by Google to support distributed computing on large data set on computer clusters. And it uses a specify a map function. A map function is there that process a key, or you can say value pair, to generate a set of intermediate keys. Intermediate key, we are also saying value pairs, and reduce function that merge all intermediate values associated with the same intermediate keys. And MapReduce runs on a large cluster of commodity machines and highest, very high scalable, and several form of implementation in there is available of MapReduce. Those who are working in programming languages like Java, C#, and C++, in all the variant, MapReduce can be used. So this is the model. Means the complex process we are reducing. Means mapping, we are mapping, a number of parameters are coming and we are reducing to the smaller parameters. Like in simplest terminology, we can say the principal component we are using earlier for dimension reduction in traditional statistical models. MapReduce can be easily replaced by that to number of parameters can be reduced and dominating one will be derived like that. So mapping and reducing are two parts. So we are saying map. First we are mapping the thing, and the parameter we are reducing. So map and reduce are two steps of MapReduce. So in MapReduce you can use on any programming model, like already discussed, C#, C++, Java. It is fault tolerance, moving computation to data, and very scalable. So one model, he can decentralize MapReduce architecture on cloud server. You can see client API is coming, map data, metadata we are taking, reduced task metadata, and Azure blob storage PQC. This way we can reduce the thing. So here you are using Azure blob storage. So Azure is one term also. Azure you can nowadays we can also use. So application of through MapReduce, what you can do, I will suggest कि for sequence alignment number of good tools are available nowadays, but for after coming this NGS huge data sets, try to use MapReduce for sequence alignment, sordid mapping, snap identification, and RNA expression analysis. We can find number of good papers available and where they are using this MapReduce. So RNA expression analysis, a number of work people are doing, and you can see on literature also. So one technology that is very important technology, that is CloVR. We are saying CloVR. What is that? Is a new application we are using, that is Cloud Virtual Resource. Cloud Virtual Resource is a new desktop application for push button automated sequence analysis that can utilize cloud computing resources. CloVR virtual machine. In here we are using single portable virtual machine that provides several automated analysis pipeline for applicable for microbial genomics, 16S, whole genome and metagenome sequence analysis. What virtual machine is? A piece of software running on the host computer that eliminates the properties of a computer. It's just virtual, but it's not a machine. It's a software running on your computer and emulate and utilize all the properties of a computer, like processor, everything it can do. So CloVR virtual machine run on a personal computer. Can you use it on your PC, local computer recourse, and require minimum installation. And key challenge of deploying bioinformatics workflow we can put through the virtual machines also. So just to conclude the cloud part with big data, cloud computing is the next big thing in big data analytics, and which is application sharing and cost effective property. It is useful for all the, and all should make it accessible. It is very attractive technology at this critical juncture of current genomic data storage. Cloud computing is necessarily a blind stick for the bioinformatics research. It is promising technology which provides storage and access to data. And scalability of cloud to reduce traffic and cloud cryptography is always to ensure security. This cryptography has also come to ensure security in cloud mode. So to harness the cloud in a beneficial and best possible way, you need to completely rely and use the uninterrupted way. To achieve this, you need first optimize the commands in the command in order to avoid termination and recreation of the cloud instances. Cloud computing is a ray of hope to researcher and don't need to buy expensive resources to carry on your daily research. So this is the thing why cloud is I'm advocating. So thanks. Hello.
Thank you so much, sir.
So I'm stopping sharing, and any query, anything is there. So we have.
Yes, surely.
I'm stopping
Thank you so
sharing
much.
here.
Yes, sir. So again, we come to an end of this session, and thanks to Isha sir for giving such a nice presentation. It was too informative, and everything regarding the big data analytics and cloud computing was covered in that. I think all the participants got benefited of this. So it is again request to all the participants if they have any query, please ask.
Any query related to that, your queries are welcome.
Any participant want to participate in this discussion? If they have any query, please. Okay, and otherwise, I may request participant to write the queries through mail to us, or you can simply write it in comment box in the team itself. So we can get them answered by Dr. A.K. Mishra sir, and will answer it back to you. So in that way, I think it will work fine. Again, all the participants are requested to kindly put your videos on so that we can at least take a snap of it, and it will go for record purpose, and in report also we need to submit the same. So आप सभी पार्टिसिपेंट से रिक्वेस्ट है कि एक बार अपने वीडियोस ऑन कर लीजिए so that at least we can take a snap of it. Now, I would request Dr. Pankaj Tyagi sir to kindly conclude the session.
Thank you, Arvind sir. Thank you, Dr. Mishra sir. Your presentation cover all the technical steps how to use data science in the biological sciences, especially highlighted an important point, the 5V are so important. Evolution of cloud computing, open source software tools, 10 major characteristics of cloud computing, relation between cloud computing and big data and envelope ecosystems and so on. It is very, very important. And I assume the participant who is attend your lecture now no require for searching any data in the software, some websites and the books. You are encyclopedia of the AI, cloud computing and bioinformatics, sir. Thank you, sir. Thank you, Mr. Sir.
Thank you, Mr. Tyagi.
Thank you so much, sir, once again from the
Thank you
entire
all the participants.
Thank you, sir.
I think now Dr. A.K. Mishra sir may leave the meeting. Arvind sir.
Yes, sir. Yes.
Okay,
Sir,
so thank you. I'm leaving the meeting.
thank you so much, sir. So now we have one more session left in this FDP. So I would request all the participants to kindly join us back again at I would say 11:45. Okay, you are having a 15-minute break, so you can take tea and snacks, whatever you like, at your places. So thank you so much. We'll meet again at 12 around. Thank you. Hello, Pramod sir. Am I audible? Pramod sir, am I audible? Pramod sir, am I audible to you?